Thank you for joining today's webinar entitled DER and Grid Management, Putting DERMS on the Desk, presented by Jesse Gantz and Ethan Boardman from GE Grid Solutions and Alex Portilla from Pacific Gas and Electric. My name is Nakoa, and I'll be your web event specialist today. All lines are currently on mute to prevent any background noise, and please note that today's conference is being recorded. We will have a question and answer session at the end of today's presentation, moderated by Angie Reisky-Parashis. To submit a text question, locate the question and answer panel on the bottom right-hand side of your screen. Type in your question, select all panelists, and click send to get your question in queue. Finally, if you experience any technical difficulties during today's event, you may submit a chat to the host. At this time, I would like to turn the program over to our presenters. Sirs, the floor is yours.
Thank you very much, Nicola. This is Ethan Boardman with GE, and today we're going to be presenting an integrated DERM, Distributed Energy Resource Management solution that's being deployed at Pacific Gas and Electric for a DERM pilot. And I am joined by Alex Portilla of PG&E and also Jesse Gantz, a solution engineer with GE. And I'm just going to briefly set some of the context of DERM and this solution, and then we'll get right into the project description and also some nice demonstration of the software that's involved in the pilot so far. So on this first slide, just for context, I want to say that for this presentation, when we talk about DER, Distributed Energy Resources, it encompasses many types of real and virtual assets that can produce, store, or curtail consumption of energy. So that includes distributed generators, electric vehicles, demand response, energy storage, and even smart city installations. So let's go to the next slide, and just wanted to say that a DER solution has multiple components, and we see it as a multi-leg solution, and it requires DER awareness. Typically, this will be coming from a GIS and customer information system as far as where the locations of DER assets are and how they're connected into the wires model. So, and interoperability across multiple types of products, and we'll characterize it as a three-legged stool. You have an ADMS component, or Advanced Distribution Management System component, and this provides that connectivity and the physical modeling, monitoring and control capability, and the analysis of impacts on feeders, etc., that are coming from DER contributions. It's really the kind of decision maker and the closest component to real-time operations in this group of components we see as bringing up comprising DERM solutions. There's also a demand management component we're labeling as DRMS, and it would manage aggregations of distributed energy resources, program enrollment, program management, taking care of the settlements, the measurement and verification aspects. And this particular component might not be owned by the utility or managed by the utility. It could be third parties, and we'll see some of that in the ongoing presentation here. And then the third component, the distributed energy resource management piece, provides support services, if you will, like forecasts of DER and developing schedules, optimal schedules for deploying and charging, discharging batteries, or perhaps curtailing generation inputs. So these three pieces need to be able to work together, interoperate, and form the larger solution. When we talk about putting it on the Yes, we see this as a function that will be in potentially a control room, an operator of the future, not necessarily the operator and dispatchers that are doing, switching actions and keeping the lights on, doing switching today, but a role that's in the control room for the management of these activities. And that person or group of people need to be aware of what are the contributions that DER are making, and with lots of interest in the phantom or hidden load, how much of load that the utility is trying to serve or be ready to serve is being hidden at any point in time by DER contributions out in the field. We have the components that are actually monitoring what's happening and anticipating the effects that we're going to see on the wires network, and dealing with the intermittency, the vagary that can come from clouds passing over PV sites, etc. So there's a lot of operational components here, and it even includes being able to issue controls out to distributed energy resources to make them actually contribute to the overall management of the grid. And we'll be seeing some more of that in the demonstration. And the last slide in my little intro would just be a quick peek at an example of a user experience, a user interface on the desktop, which brings together different types of data from all those various pieces we talked about, as well as external sources like weather forecasts, etc., and provides not just a dashboard view, but also has some underlying analytic capability to present more actionable information. And we'll see some more of this as we proceed on. And with this, I'll hand it over to Alex to talk about the PG&E project in particular.
Thanks, Ethan. So with that, before we jump into the project, I'd like to set a little bit of context in the PG&E world. And the way we look at distributed energy resources is we see challenges, but we also see great opportunity for PG&E. So we have a set of different DERs, and I would also lump energy efficiency into that category, even though it's not a dispatchable DER, but also kind of put that into the same category. So when we see, what we have in PG&E service territory, and you see this in other places in California and in Hawaii, is huge growth. So what we're expecting is 200 to 400% growth in distributed solar. That's for us, that means an additional 400,000 to 800,000 systems, rooftop solar, in our service territory by 2020. It means significant growth in electric vehicles, and it means lots of storage. So 290 megawatts of distribution-connected storage by 2024 out of our overall mandate for 580 megawatts. So we will have a lot of DERs connected to our distribution system in the near future. And at the same time, we're looking at not only accommodating those DERs, but there's a number of regulatory drivers and proceedings that we're active in that are looking at not just how do we accommodate DERs, but how can we actually use the inherent value of DERs for benefit of the grid, benefit of our customers, as well as facilitating participation of those DERs in wholesale markets. And so there's a number, this is just an example of a little bit of alphabet soup of some of the activities going on in California that you might want to take a look at. But essentially what we're trying to say here is there's a lot of change happening, both from a technical standpoint, but also from a business standpoint, and we're looking to work our way through that. If you think about what that means kind of more concretely on the grid, here's an example of what DERs can impact. This is loading from a bank, October 23, one day, so you can see kind of a typical evening peak here and a typical load curve. This is an October day in 2013. And then you see here that same day 3 years later. And this is the loading at the bank level. And so pretty dramatic shift in how the grid is operating. And this isn't from intermittent solar. What this is a distributed battery that is participating in the wholesale market as a regulating resource. And what this 4-megawatt battery does essentially all day long is it goes from full discharge to full charge in a matter of seconds. And so really how we operate the grid in the future, where these types of assets become more commonplace across our system, requires a new tool set. And so it's changes like this that are leading us to embark on this new journey of exploring DERMS technology and business models for how we interact with DERs. And so kind of bringing us to this project, we're really working with a number of collaborating partners to deploy a fleet of distributed energy resources. In this case, we're working with GE as the solution provider for the DERM system, and we're working with Solar City as a provider of photovoltaics with smart inverter control up to 250 kW that we're putting out here on a limited geography, so it's 2 feeders for this project. We're also working with distributed aggregations of storage. So we'll have storage, residential storage, so Tesla Powerwalls in people's homes from Solar City, as well as C&I, so commercial storage, behind the meter in an aggregated fashion. And then kind of to round out our fleet is we're using this 4-megawatt battery that is a utility-owned battery that is a market participating resource today, and so we'll be using this resource as well. And our primary goals here are to map out the processes of how we interact with a fleet of resources to provide distribution level services. So we're really focused here on solving potential issues on the distribution system using aggregated DERs, and Jesse will go in a little bit later into how we do the aggregation and how we interact with the specific assets. So I'll spend a little bit of time going through the use cases. And the first use case is really a modeling use case. It's demonstrating and visualizing for operators what the DERs are predicted to do on the system. So particularly around solar, distributed solar, solving the load masking issue or visualizing the load masking issue so they can see what is not just the expected net load on the system, but also the gross load in case we lose the PV. The second use case is, I think, kind of the core of our project is really looking at capacity constraints all the way from the substation down to an individual device out on the feeder. So if there's an overload, can we solve that overload by dispatching batteries, for example? Or if there's a reverse power flow situation, we could solve that solution with raising load, so charging a battery, or if necessary, kind of last resort scenario, curtailing PV. Then we have some voltage management use cases. So mitigating voltage issues, you can do that obviously with by changing the load, but also using the inverter settings to manage reactive power. We'll also be bringing in an economic element. So Jesse will talk a little bit about how we bring in different inputs, but it is a market-based optimization, and so we will be doing least cost dispatch of the resources, and so there's the economic element of it. And then operational flexibility, as we get more complex, is looking at if there are switching or abnormal states on these feeders, can we re-optimize and redispatch? And in the long term, the promise there is, can we restore more customers faster due to the presence of DERs? So we'll be exploring that use case. And then the final use case is really underlying everything is looking at performance verification of not just of the DERM system and the modeling within the DERM system, but also looking at the entire flow of information. In the future, what are the latencies that we need from a communication standpoint all the way down to the individual asset? How well do assets perform when they're called upon? Because the future promise of a system like this means running the grid very differently, and we need to ensure that the reliability is adequate if we're going to do something like deferring a capital upgrade of, if we have load growth, deferring a capacity upgrade. Because of the presence of DERs, we need to be sure that those DERs will deliver. So we have kind of a strong verification analysis underlying the entire project. So with that, I think Jesse will take us into a more in-depth look at what the system is, the actual system being deployed, and run us through a demo.
Okay, thanks, Alex. So I'm going to start first with the architecture of a DERMS solution and look at some of the key components that are involved. So, one of the requirements that we'd say we have from the customers that we work with is a modular solution. So not all utilities have all of the necessary components or have them available for integration. So we want the DERM solution to be agnostic of the other legs of the stool that Ethan was talking about. So if we look at a demand response management system, or DRMS, we recognize, that's not available everywhere. That may be managed by third-party aggregators. So that should not be a requirement for having DERMS distributed resource management functionality. But where it's available, it should be leveraged. Separately, for the ADMS, or the real-time management of the distribution system, that's an advanced technology, again, that may not be deployed everywhere. Where that's available, that should be leveraged. There's an as-operated network model. There may be switching information and power systems analysis applications that can be leveraged. But again, we should be able to derive some benefit from a DERM system even without an ADMS system. So you can see from this diagram here, there's an IT-OT integration layer separating that from the DERM solution. Within the DERM solution itself, the core is focusing on providing situation awareness, operator control, and reporting to the human user at the high level. Under the hood, there's lots of functional components. I'd say the key ones and specific to DERMS are the forecasting of load and output of distributed energy resources, and managing multiple forecasts and aggregating those forecasts. So if I have a forecast at an individual, residential PV site, that's great, but a human user doesn't want to look at that level of detail. They want to roll up to a key switch in the network, or they want to roll up to the feeder head or to the power transformer, to the substation. So it's the aggregation of that forecast information. Is also the disaggregation of the native load and the net load. Look-ahead analysis, this is taking forecasts and running some analysis on that. So in the case of the PG&E system, there's a power flow solution that's available both against the real-time system, but also to use in an offline study environment to do analysis and identify where there's low voltages, where there's going to be overloads at every point in the network. The aggregator dispatch, this is where there are third-party aggregators involved that have dispatchable resources, having an interface to them to send controls so that they can then send them to their individual DR resources. The most advanced part of the DERM system would likely be the optimization component. So this is taking the forecast, the look-ahead, the constraints in the system, the economic inputs, and then running an optimization against that. And by optimization, this is a scheduling problem that we're trying to solve. How do we schedule these resources over the next 12, 24 hours to resolve current and anticipated problems? And then once we have a solution, it's been vetted by an operator, that dispatch needs to be sent out. So if these are SCADA-enabled devices, it could be through SCADA control, but more likely it could be through an aggregator interface or using kind of non-SCADA protocols like OpenADR or IEEE 2030.5. And of course, in order to do the look-ahead, the optimization, we need a model of the system. So this, at very minimum, we need a model of the DR that on the network and how they're topologically connected and can be aggregated up. And ideally, we have some power systems equipment information as well so that we can run that full power flow analysis and calculate voltage and calculate current at every point in the network. So that's really the logical application side of this. There's a field communications component where we're talking to individual resources. And then there's also a lot of interfaces to other systems. So we're going to walk through the different interfaces that are deployed for the PG&E pilot. But you can see here listed there's GIS information, and this is typically for utility-owned assets, but now we're looking at a lot of behind-the-meter customer-owned assets that also need to be added into that model. So that may even come from a different source system, such as an interconnection database. To get the real-time loading of the system and to kind of initialize the forecast, we do need to have some real-time SCADA data coming in where that's available. AMI is great for looking at individual customers' demand, potentially identifying low or high voltage. It can be used after the fact to validate that controls have been sent. Market interfaces, so this is for wholesale markets where that is used as an input into the optimization. We need to be able to pull down that data. Weather forecast, third-party aggregators. These are some of the other interfaces that I've discussed. And then finally for CIS and DR registration, this is kind of that more of a demand response system type functionality, but the whole idea of managing programs for participants to enroll and participate in so that they can be compensated for providing the flexibility of their resources. So managing those programs. This is a high-level view of the functional blocks and how they fit together. So for the PG&E DERM solution, this is, I'd say, one instance of a DERM solution. The external interfaces that we've implemented are a read-only SCADA data interface. No controls are going out through SCADA, but this is providing us loading, voltage, switch status, at all of the electronic switches and outside the substation as well as inside the substation, and we'll be adding some data cap information as well. We also have an interface to the system that is managing the state of the network, the as-operated model. So we're no operators using the DERM system to perform switching or manage cuts and jumpers and tags like that, but we do need to know what the current state of the network is. So we read that information from an interface where the SCADA status is not available. PG&E has a meteorology department that actually has its own internal weather forecast service available, as well as a solar forecast service. So in this case, we were lucky we can kind of hook up to that and get forecasted PV output over a pretty long time horizon at each individual residential site. So we have very high granularity forecasts for PV. We're connecting to OASIS to bring down the day-ahead market LMPs from CAISO so that we know the cost of energy, and that can be used in the optimization. Like Alex mentioned, there's a 4-megawatt network battery that has its own interface, so any dispatch to that needs to be using that custom interface. And then finally, one of the larger parts of the project from an integration standpoint is development and deployment of an interface that uses the IEEE 2030.5 protocol to communicate with the aggregator participants. And I'll talk a little bit about that interface later on. Just to quickly recap some of the functionality I discussed previously, the core features of the system for the PG&E system are running an online power flow analysis against these two distribution feeders, running a volt-var optimization using only inverter-connected DER resources, so not using the traditional capacitor banks and tap changing transformers, but just looking at inverters as a controllable resource and using reactive power to mitigate voltage problems. We have a load forecast function, and the load forecast and solar forecast are fed into this time series power flow solver to perform the look-ahead studies. Separately, there's an optimization engine for identifying both grid needs and how they can be met with DR flexibility, as well as actually performing the scheduling, the optimal scheduling of the DR. With that engine, we're able to basically run two types of markets for the participants. There's a day-ahead market that's run once a day with very specific gates. That's really three key gates. One is the DERM system will calculate the needs of the distribution system. I have a low voltage here. I need this much flexibility to resolve that. It will publish that to the aggregators. The aggregators have an hour to respond with a bid. And then after the close of that bid gate, then the market will clear, and then the dispatches will be reviewed and then approved. And once they're approved, they'll be sent to the aggregators to work into their next day operating plan. So that's what we mean by a day-ahead market. Separately, we want to not just be solving tomorrow's problems, but any problems that can occur right now. So that's why we have an ad hoc intraday optimization as well that runs against kind of a rolling forecast of flexibility from the aggregators and a standing price associated with the flexibility dispatch, so that can run to resolve problems as they occur during the day. Finally, there's the ability to manually dispatch DER. So to take advantage of some of the smart inverter control modes, and obviously to be able to present this data to the user and to allow for them to perform some operation through the system. Okay, so I'm going to quickly go through the modeling of DR. So if we look at a very simplistic view of the network, we've got a substation with one feeder, with one SCADA switch, and some DER. We have some solar and some battery here. So this is the actual physical assets. So we can aggregate some of these together to create an aggregated DR resource. And the advantage of this is creating a larger dispatchable unit for the utility operator, as opposed to thinking about sending controls to 10,000 rooftop solar PV inverters. Maybe they could just have 50 controllable resources that are going to that they need to manage. So the definition that we're using for this project for an aggregated DR, they need to be from a single DR operator or a single aggregator. They need to be of the same type. So they need to be either all solar, all storage, or a mixed type asset. The DR operator is going to need to be able to provide flexibility forecasts and bids for this aggregated DR as a single unit. And they'll also be dispatched by DERMS as a single unit. And obviously not all DR need to be rolled up into an aggregated DR and participating. So that's what these few units at the end of the line represent. So when we get closer to the market concept, we define what's called an aggregation area. And there's a lot of work being done in the industry right now around grouping and aggregation of DR resources. But this is really the definition that we went with for this pilot project. We define an aggregation area as a geographically and electrically distinct area where DR or aggregated DR from multiple operators can participate. So the process is the utility will define the boundary of this area, and then the DR operators will kind of enroll their participating resources into a given area. And the DERM system is going to publish needs to the aggregators for a particular area. So I need 100 kilowatts down flexibility during these hours of the day in this area. And that's what the aggregator will receive. And then they will, the user will also be able to view flexibility needs and bids and resources by area as well. So it's kind of a roll-up. For this pilot, it's a non-hierarchical, it's not overlapping. It's just a distinct footprint. And so one more slide before I segue into the demonstration, but I want to talk a little bit about this 2030.5 standard that we're using. So this is kind of formally known as the SEB 2.0 protocol or Smart Energy Profile. So this was selected for the utility to aggregator communications. The DERM system in this case is not communicating directly with any devices. All control is through the aggregator, with the exception of that one network battery. 2030.5 has been recommended by the Smart Inverter Working Group as the default protocol for smart inverter communications for California Rule 21. So there's a lot of momentum and support behind this particular protocol. And one of the reasons that we were interested in it was because there's a rich feature set for inverter monitoring and control. So what we've implemented for this project are 4 kind of commanding or control capabilities to inverters. One is the ability to connect or disconnect. The next is to be able to send a power factor set point. The third is to be able to limit the peak power output. And the fourth is to be able to dispatch generation up or down by a fixed amount. And for each of these 4 control modes, we define them in event windows with a specific start and end time. So we will schedule a power factor set point event from this hour to this hour. In addition to these commanding capabilities, there's the capability to retrieve status and settings for DR, as well as forecasts and dispatch schedules for these aggregated DR. So it handles that, that aggregation of DR very well. Okay, with that, I'm going to share my screen, and I'm going to give a brief demonstration of the DERM system. Okay, this is a live demonstration, so bear with me if there's any kinks. Okay, so this is a demonstration model. We're not looking at the PG&E system. This is a simplified version of what has been deployed. But it's got the same look and feel and the same key information that's being presented to the DERMS user at PG&E. So on the left-hand side, what I'm viewing here is a geographic view of the network. This is obviously, the electrical information. I've got substations. We're going to be focusing on this Muirfield substation here. The lines leaving the substation, this is just primary network. The coloring is by feeder. So that's why this one yellow feeder here has a lot of solar resources at the end. I can click on them and see the rating as well as the current real-time output as provided from that solar forecast service. I can look at an individual line's phasing, conductor model, real-time flow, and limits. So this is really that power flow information that you would get from an ADMS system. So this is my network view right here. We're looking at an area along the coast. So I'm going to turn on a background layer. This is a way an operator can turn on some overlays to show temperature or weather or cloud cover to just give a little bit more situational awareness. But if we go back just to the network view here, we're going to focus on the electrical side. So what we're looking at in the center is a forecast of the loading on this power transformer in your field substation. So you can see the vertical line here represents the current time right now. The history is what has been saved in the system for the historical loading, but we're looking forward 36 hours into the future. That's our forecast window. And we're showing two traces. So one is for the net load, and by net, that's what SCADA might be telling me at that location as the loading on that bank right now. The native load is what the true load downstream of that bank is. And the difference is due to the fact that we have DG locally supplying a lot of that load. So if we want to look specifically at the DR forecast, we can say we have a couple of different types of assets that are injecting into the network. Solar following a regular solar profile during the day. So that accounts for the gap between the net and native load. A couple of the other widgets that we have on this display are showing some real-time alerts on the system where the operator might want to direct their attention, kind of a high-level snapshot of the health of the system, a list of where these optimization plans will show up, and then finally what the dispatch of flexible resources is currently in the system. So the use case we're going to look at is, let's say that right now we have a solar forecast that says it's going to be a cloudy day, and I don't have as much solar as I potentially could. But the meteorology department changes their forecast, and all of a sudden I'm going to get a lot more solar on the network than I anticipated. And I'm going to see a jump in that output. I'm going to see a change in the net loading at this point. So you can see all of a sudden I jumped from 3 megawatts to 8 megawatts solar during the day. And that's going to cause a backfeed in the near future. And this is a non-reversible flow bank, so I have a hard limit at 0 megawatts on that bank. So I've got a problem now, and that's been indicated as a backfeed alert that's forecasted. I could turn on a layer here to show physically where are these alerts going to occur, or these issues going to happen. I've got a backfeed here, and because a lot of solar is towards the end of the line, I could expect the voltage rise and some high voltage issues at that location. So the operator at this point knows they're going to have a challenge in the near future, and they could look at what sort of resources do I have. So these are these aggregation areas, and if he or she wants to look at what sort of resources are in that area, they could select that area. They could say the total connected capacity of flexible resources is this amount. These are the two aggregators that are participating, and here's our controllable DR. And here's what they've reported is their flexibility for the next 36 hours. So I can see that I might have some battery resources that are able to charge, discharge, and potentially some curtailable solar right here. So this is generator reference. So this is an inverted solar profile, meaning that I could potentially curtail this much solar, and it's stacked by the individual resources here. So if I wanted to look, I can bring on and off the different resources. So, basically the operator at this point knows there is some flexibility in the network to play with, but let's let DERMS go through and determine what the optimal solution is. We're going to run an optimization, and DERMS is under the hood taking into account all of these market inputs, the forecasts, and coming up with a plan. So you can see the new plan arrives, and I'm going to view either the kind of technical information about that plan, the power systems kind of results from the analysis, or the economic side of the picture. So this might be two different types of users looking at that information. So let's first look at the technical side. So this display was designed to be a one-stop shop for viewing all of the information needed to assess if this is a good solution. On the left-hand side, we're looking at that power transformer again, and we're looking not at just the current forecast, but also what the optimized loading on that bank could be. So you can see that after we implement this solution, this is how the loading is going to look. So we're reshaping the load curve. So that's that one backfeed violation, but we had some low voltages as well. So if we want just a simple count of the occurrences of voltage and backfeed and flow violations, this top graph here shows us before and after how many problems we're going to be having, and those are also listed here in a tabular form. So I've got some low voltages, and I've got that backfeed on the bank. And then after the solution is implemented, this is what I'll have left. So I've got a before and an after in most of these left-hand displays here. On the right-hand side, I'm looking at what DER am I dispatching to achieve this change in load shape. So I'm stacking multiple resources here to kind of to shave that load, and you can see I have some from my two aggregators, Solar Charge and Green City, using fictitious names, as well as the utility network battery there. So we're calling them multiple resources and stacking them. These are the dispatch schedules that we're going to send out once this is approved. So in the PG&E pilot, all control is advised or reviewed by the operator before it is dispatched. So we have the button down here to allow the user to kind of go through a confirmation that they want to send that control out. So I'll send that out, and then separately, if they say this is not a good plan, I'm gonna go and do it differently, they would be able to manually send some controls by navigating to another screen with this manual dispatch button. Before I look at what that dispatch effect on the forecast and the rest of the system is, I want to look at the economic side. So again, this is a different view of the same plan, and as Alex mentioned, this is performing a least cost optimization. So we're converting all of these constraints into dollars that we're trying to minimize. So in this screen here, this is kind of a roll-up of the optimization before and after results and a tabulation of them. We can see that, so as part of the day-ahead market clearing at this time, in the economic results sections, we see we have the wholesale cost of energy. So in the columns 1 and 2 here, we're looking at megawatt-hour energy use, and then we're looking at the corresponding dollar amount here. So this is taking the day-ahead market LMPs times the loading over the next, over the optimization horizon. We're also looking at what aggregator resources have been selected. So we've got some Solar Charge and some Green City down flexibility that's been activated, and it's going to come at this cost to the utility. And then finally, we have some utility assets. That network battery has an operating cost or an opportunity cost to charging and discharging. So since it is being called upon, there is some cost associated with that. And then finally, since we're trying to mainly solve network problems or overloads, low voltage violations, backfeeds, we need to assign a cost to those. And so we have a count for how many issues are occurring, but more importantly, we have a proxy for how much is it costing me to have a volt excursion outside of a limit for an hour, right? So this is really the unit of the cost for a voltage violation here. So dollars per unit voltage outside of the band for an hour, and same for flow. We can have a cost associated with a violation so that we can get a total cost for the state right now and afterwards, and then compare those. Finally, this shows the tabulation of those results to see that the delta should be a reduction in cost. And the bar chart here just shows the flexibility that was awarded by aggregator type. And for the user, they can kind of compare the planned dispatch schedule to what the wholesale market prices are to see how well this is aligning with the wholesale market. So again, this is a view of the economic side of the plan. So previously I dispatched that plan. So let's return to my home screen. And at this point, I see that my forecasted violations have been resolved. My planned state is now dispatched. And if I look at the forecast here, I see that my net load curve has been shaved to prevent any backfeed during these hours. And to achieve that, I'm actually charging and discharging a battery. But where I don't have any more battery capacity to activate, I had to curtail about 1 megawatt of solar here. So this shows the after case. The operator now knows that DERMS has gone and sent these controls out, and the system's in a much better state. Okay, so that concludes my demo, and I will go back to the slideshow at this point.